All right, welcome to Module 5, and we are discussing quantitative analysis this week. So we will discuss chapters 9, 10, 11, and 13. And remember, for this week's assignments, hang on one second. Oops. That's okay. For this week's assignments, remember, you only have to do the quantitative analysis worksheet if you are using the quantitative analysis for your final project, okay? Sorry, my dogs are playing in the background. I apologize. So we talk about numbers into statistics, which I realize you were just asked about. Oh, no, you weren't. Okay, never mind. Sorry. Multiple thoughts going on in my head at any time. Hang on one second. Okay, sorry, I had to tell them to quit arguing. So we talk about numbers into statistics. So we talk about raw data. This is just the numerical numbers that they put in. So if you're using a Likert scale 1 to 7, right? I put a 4 for this and a 3 for that. It's just those raw numerical numbers. The data set itself is the collection of that raw data of the same variables for the sample of participants. So we collect everybody's answers for this one variable. The descriptive statistics convey essential information. It is all about each variable and the data set as a whole. So this many women participated, this many men participated. You can get your how many were freshmen, sophomore, junior, seniors, all of those in this type of statistic that we use. Fun fact, I always mix up descriptive and statistics, and so does my former colleague and friend, Dr. Brenda Rourke. And so we constantly in SPSS are like, wait, which one do we click again? Because they all kind of are so similar. Sorry, off on a little tangent, but it's, related at least. So then we have our inferential statistics. So this is going to provide the information about the relationships between variables, among variables, and that helps the researchers draw those conclusions because they examine the data in the sample, right? They're looking at the relationships. We can definitively say that this many people interacted with each other or whatever relationship you're exploring, okay? All right, we talk about a normal curve. We're talking about bell curves, so, up and then down. Theoretical distributions of scores on in their numerical values or other numerical values. So a normal bell curve is going to be completely over the center. We like to think about bell curves a lot in grading, where you would have similar amounts of A's and F's, B's and D's, and then C's right in the middle. So skewed distributions are going to be distributions that aren't normal. So they're not that perfect bell curve. We can have positively skews, which the distribution is going to have very few scores on the right. And then negative skewed is the distribution is going to have very few scores on the left. So let's say we are talking about undergraduate education and we have a positively skewed curve. And I know it might look like it's my potentially left hand up, but this is my right. So the positively skewed, you're not going to have very many scores over here. Okay, so you have more F, Ds, and Cs. You have a couple Bs and As, but they're all skewed over to the left. And vice versa. Maybe you have an undergrad class that is really good. So it's negatively skewed, which sounds backwards, but it's negatively skewed because there's not very many scores over here. You have few F, Ds, Cs, but you have a lot of A's and B's and then leading into C's, okay? So let's talk about descriptive statistics. First, the number of cases. The greater the number of cases, the more data points that we have, the more reliable the data. Hey, stop biting that. Sorry, my dog is biting my cast iron sewing desk. Rambo, stop. So if we have more data points, if we are able to collect data from 200 undergraduates versus 20 undergraduates, our data points are going to be more reliable. Dunstan, quit. I'm so sorry. Dunstan, stop. Central tendency is this summary form of data, right? This is just kind of what we're seeing generally, this summary. The mean is the average. We combine all of the scores and then we divide it by the number of cases. Guys, get out of there. The median is the middle of all of the scores of one variable, and then the mode is the score that appears the most often in that data set. We talk about range, and these mean, median, mode, range, you probably learned back in 5th grade, so I'm going through them quickly. They're not the ones that typically trip people up. Range is the value calculated by subtracting the lowest from the highest. Your standard deviation, this is where we really focus on standard deviations and, oh my gosh, and means for quantitative descriptive statistics. So the standard deviation is the standard calculation. It is a representation of the variability. So if we talk about having mostly the mean for the class is a B minus, right? So the average is a B minus. The standard deviation might be 0.5. That means that in either direction, it's going to skew. It's got that calculation that shows that variability. About on average, scores for the average makeup of this test or whatever skew between a B minus and a C and a B minus and a B, right? That's what that's saying. Hang on 1 second. Okay, sorry about that. So that's the standard deviation. How much does it deviate from the average? Okay. Frequency is the number of times that we see that variable occur or that value in the variable occur. And the percentage is all about comparing between the baseline, any number, and a second number that we use to compare at the base. Okay. So with percentages, it's like, hey, here's the percentage of everybody. The average percentage on the score was a 72, right? But then you want to talk about, let's compare that to the base. Well, you got a 96. So that means that you did 24 points, percentage points possibly on that. So again, easy, but had to go over it. Okay, so we talk about significance levels. Hang on 1 second. Sorry, I just decided to move it, so hopefully they won't be able to get to it as easily. So significance level, it is criterion for accepting or rejecting hypotheses based on probability. So how definitive can we be? How sure can we be that we can accept or reject this hypothesis? Okay, so probability. This is an estimate of what would happen if the study were going to be repeated multiple times, and it tells the researcher how wrong the results can be. Okay, so this is what we're saying would happen if we did the study 100 more times, and we can show that the results would stay the same. It would not be very wrong. We have a population inference. So we accept this conclusion from the sample, and we assume that the conclusions are also applicable to the population. So what we're saying is, we can accept this conclusion because it is applicable to that population. I can say that because it is this sample and those conclusions apply to this population, I can accept this conclusion for the entire population. If that makes sense. We have process inference. So the data is consistent with the predictions the researcher drew from theory. So this is what we see a lot of the time with quantitative research is the process inference. We have seen theory and background and we understand what's going on. So we've made those predictions. And from there, we follow the scientific process and then made those conclusions. We have probability level. So this is also called the significance level, and it is the level of error that the researcher is willing to accept. So a lot of places are kind of getting away from significance levels. Like, not that they're getting away from using it. I don't want to say that, but P-scores were, widely used as this exactly shows what we want. And now they're finding other scores to add in with the significance levels, the P levels, to make sure that, so yes, you do need to know this and stuff, but just know that there are other levels and scores that we add with it a lot of the time. So probability level. So it is our significance level and it's the level of error that we're willing to accept. Usually it's P is less than 0.05. So if you have anything in your study, let's say it's P equals 0.054, you cannot say that you have significance because it's bigger than 0.05. Right? So let's say P is equal to 0.27. You could say that you have significance at the P is less than 0.05 level. If you have P is less than P is equal to 0.001, you could say it's at the 0.01 or 0.001, depending on what the level of significance is, okay? Alpha level, that's your probability levels, and that's your P level. So the alpha level is the actual number that we're willing to accept. P is less than 0.05, P is less than 0.01, P is less than 0.0001. Nope, 0.001, not 0.0001. Then we start getting into social significance. So we talk about having social significance in application. We have a large sample size, and that can give us statistical significance in our research. But social significance is going to state that the applicability is also relevant. Okay, so we've talked about kind of skewing the numbers in your favor, where you survey 10,000 people. You find a really small significance, but it's there. But if you'd only surveyed 1,000 people, it probably wouldn't have been there. Now, that's an error, or that's an issue that we worry about. However, social significance is saying, yes, we do have a large sample size, but based on this social concept and based on this direct population, its applicability is relevant. Maybe studying something about Taylor Swift, right? If we talk about Taylor Swift fans, we could easily get tens of thousands, maybe even hundreds of thousands of people to take a quick survey, right? But even though we have a ton of people, it's still relevant. Okay, Stanley, get out of my, sorry. Now we're going to talk about two types of errors. First, we've got type 1 error, and this is the null is rejected even when it is true. So the null is just the opposite of your, okay, I shouldn't say opposite, that's confusing. The null is basically stating that there is not any sort of variation or anything that you're going to find in this data set, right? So if I predict that Taylor Swift fans are bigger fans now because of Travis Kelce than when she was with any of her, there are more Taylor Swift fans now than when she was with any other ex-boyfriends, or they're more satisfied, whatever it wanted to be, right? I'm going to say they're more satisfied now with Taylor Swift that she's with Travis Kelce than when she was with any other previous boyfriends. So the null is just going to say there's not going to be a difference in satisfaction between Taylor and Travis versus Taylor and Joe Jonas or wait, was it Joe? I don't know. Whoever she's dated in the past, right? That's type 1 error where the null is rejected. I say, yes, they are more satisfied, but there's not actually enough data to support that. The null is actually true. And it happens sometimes. Type 2 error is the null hypothesis is accepted even when the alternative hypothesis, so our prediction as the researcher, is true. So the data is being weird, and it's showing that Dunstan, quit. The data is being weird, and it's showing that Taylor's fans were actually more satisfied with the X's than they are with her and Travis. But that's just what it's showing, like through the research or whatever. But really, our prediction was true. She is more satisfied, or the fans are more satisfied. Okay. We have a lot of things in place to kind of avoid these type 1 and type 2 errors. So they happen less frequently, but they do still happen. All right, chapter 10, talking about inferential statistics. We use these to draw our conclusions about a population by examining that sample. So we have degrees of freedom, or parentheses, DF, parentheses. So this is the way in which the scientific tradition accounts for variation due to error. So with inferential statistics, we want to make a conclusion about an entire population from this sample. So my inferential statistic, I want to say the entire population of Taylor Swift's fans are more satisfied with her and Travis than they were with her and any X, right? So we use this to draw those conclusions. Hang on one second. They're starting to get a little. Okay, so the degrees of freedom are going to be what we're going to use to account for error, right? This is what I was just saying, as we have different things in place to make it easier so we don't. So degrees of freedom, we're making these conclusions, and in this, it's just another step that shows, okay, we're making sure that this isn't due to chance or error. This is actually what we're seeing, okay? We talk about chi-squares, and we use these to determine whether the differences are going to be statistically significant, right? So Taylor and Travis, Taylor and insert X here, right? Those are our two groups. So we have two groups. You can have more, but typically, maybe not with chi-square. I'm going to leave that part out. I'm not going to. Guys, hey, Stanley, quit. Sheesh. So we want to see if there are actually differences between the two groups. Then we talk about observed frequency. So the number of times this category actually appears. So satisfaction with Taylor and Travis, satisfaction with Taylor and X, right? How many times does it actually appear? And then the expected frequency is how many times the category was expected to appear. So we think that satisfaction with X is going to be low. So we expect that it's going to be, if we're surveying 100 people, I'm going to say it's low, like 25% of people, right? So we expect that it's going to be very, very minute. But maybe the observed is actually much higher. Okay, so that is chi-square. We're going to talk a little bit about one-dimensional, or one-way and two-way. Oh, dimensional, I have it right. Okay, so with one-dimensional, we use this for determining the differences in how the cases are distributed across the categories of one categorical or, oh my gosh, or nominal variable, and if they are significant, okay? So what this means is I want to see if there are differences between satisfaction, Taylor and X, Taylor and Travis, okay? In a one-way categorical nominal variable. Oh, that's not categorical. Well, yes, I could call it yes or no. Satisfaction Travis, yes, no. Satisfaction with X, yes, no, right? And I want to see if there's a difference within each themselves. So I'm not comparing the two groups yet. I'm just saying, okay, satisfaction, is there a significance between were they satisfied or were they not satisfied with Travis and the or Taylor and the X? And then I'm going to do the same thing by itself with Taylor and Travis. We have a contingency analysis, which is two-way, two-dimensional chi-squares. And we use this for examining the association between the two nominal variables, okay? So we've got the difference between the Taylor and X and Taylor and Travis for satisfaction. Now we're going to compare the two, satisfaction with X, satisfaction with Travis for the fans, okay? And then the contingency table is just displaying that data to your audience. Dunstan Stanley, quit. All right, chapter 10. Oh, we're still in chapter 10, sorry. T-tests. So we use our test. Nope. Wow. We use this to test our hypotheses. Hang on one second. Okay, so we use these to test our hypotheses that we expect to find differences between groupings of independent variables on continuous dependent variables, okay? So we've got independent samples t-tests. We calculate them according to sample size for each of the two categories, okay? So satisfaction, because we might put it on more of a continuum. It's the Likert scale. It's not yes or no. Okay. So we're going to calculate according to sample size, each of the two categories. Okay. Paired samples. We are going to use these to compare two paired or matched scores. I'm not so good with paired samples t-tests. They always trip me up. So I know that we have two matched scores. So that would probably, my example would probably actually be a paired samples t-test, because independent would be, well, no. I don't know. Paired samples kind of trips me up. So if you get caught on that and you're struggling with it, chat with me, and then I don't have my book with me right now, but I will get my book and read further into it, because again, that one does trip me up. Two-tailed t-tests. This is when a researcher asks research questions or states their hypothesis, stating there is going to be a difference, but they're not stating which direction. So the two-tailed t-test would be, there's going to be a difference between satisfaction of Taylor Swift's fans from when she was with her ex versus when she's with Travis, right? I'm not saying that people are going to choose one side or the other. I'm just saying that there's going to be a difference, okay? One-tailed, however, is going to be a specific difference that's going to be identified. So Taylor Swift's fans are going to be more satisfied that she is with, or since she's been with Travis, than they were with her music when she was with insert X, right? I'm saying that her music is better now. We're more satisfied with her music because she's with Travis. She's happier. It's a healthy relationship, whatever it is, than when she was with X. Okay. All right, ANOVA, which is analysis of variance. So this is all about how much do things vary from each other. So it compares the influence of two or more groups, the independent variable, on the dependent variable, and represented by the symbol F that is capitalized and italicized. So variance is going to be the dispersion of the distribution of scores. Okay, so How do scores vary? How do the dependent variable scores vary? Okay, how are they dispersed? We have planned comparisons. So these are comparisons among groups that are indicated in the hypotheses before the data is gathered. So guys, quit. So a planned comparison, I'm going to say I am going to compare the groups of satisfaction, Taylor with X's, Taylor with Travis, right? I'm telling you that in my hypotheses. We have a post hoc comparison, which is conducted after the researcher finds that there is a significant ANOVA exists. So post hoc comparison, maybe they didn't know what they were looking for, and therefore they ran an ANOVA just to see what they could put in there, and they found some sort of cool study, right? So with that, I just did a study on trigger warnings on TikTok, and we found some really cool post hoc comparisons, some post hoc analyses. Basically, what we had found is because we did not know really what emotions were going to come out. I couldn't say definitively, yes, it's going to be fear or anxiety. That's what I did think because of research, but we didn't find that. We found anger and empowerment, and these are really cool, but they are post hoc because I didn't put that into my study, because why would I have ever guessed that this type of relationship exists? Okay. We have between groups variance. So the groups vary enough to distinguish themselves from one another, right? So comparing Travis and X, right? There's enough of a difference in satisfaction that we can show that they have distinguished themselves. We have within groups, the variation among individuals. So not just groups, but the individuals themselves within any category or level. So what's the variation of the actual participants of the sample? Okay. All right. So going with ANOVA, between subjects design, kind of like we talked about a second ago, each participant is going to be measured at only one group or category and only under one condition. So you cannot be measured as Taylor's X and as Travis. They are completely separate, and they are going to be measured at only that one group or category under that one condition. Within subjects design is going to measure each participant more than once, usually at different levels for different conditions. So if I wanted to do satisfaction with Taylor Swift and X's, I probably should have started this when Taylor Swift started going public about dating, right? And I can measure each participant at every time Taylor gets a new boyfriend or whatever, right? So every participant in my study is going to be measured once. Oh, my last example didn't work. Every participant in my study is going to be measured once. So I'm going to measure them when Taylor dated the ex, or when she's dated Travis, not both. And then within subjects, I'm going to measure you at every single boyfriend Taylor gets. So you're going to get measured multiple times for different conditions. Okay. One way ANOVA is going to test for significant differences in the dependent variable based on categorical differences in the independent. Okay, so satisfaction increases because you said yes, you were satisfied, or you said no, you were not satisfied. Okay. Two-way ANOVAs, two categorical independent variables, and one continuous level dependent variable. So this is going to be similar, categorical independent variables. Satisfaction, yes, no, and continuous level, or boyfriend, Travis or whoever, and then satisfaction, 1 to 7, stuff like that. That was 2A. Then we get into eta squared. This is the assessment of the proportion of variance. So it's just to assess the actual variance in the dependent variable that is associated. So it's saying that the variance is, like we're going to assess, is this due to chance? Is this due to actual assessment in the study? Okay. All right, chapter 11, we talk about testing for relationships. This is where we talk about linear relationships. So one unit changes in one variable should be associated or are associated with a constant change in another variable. So as other variables increase by 1, that's going to be with change that's happening in the other, right? So they're moving together or they're moving apart if that's what you have expected to happen. Okay, so if I say they're going to separate, as this variable moves once over more and more, this variable is going to keep moving this way too, because that's what we predict. Okay, curvilinear is going to represent that U-shaped curve. So it's going to be kind of the upside down bell curve. But linear is we can draw lines and kind of see all the associations. So we're going to talk about correlations. This is a statistical test that examines linear relationships between two continuous level variables. Correlation is all about relationships. Do they associate with each other? So we have a spurious correlation. So there is a 3 in the word tested that's not supposed to be there. Sorry. Spurious correlation, one in which a third variable is influencing the variables tested. So spurious correlations, these are kind of my with this, it might be, oh goodness, what was the example? Oh, ice cream sales and murder, right? Or crime rates and Mother's Day. As crime rates increase, or as Mother's Day continues on, crime rates decrease. As ice cream sales increase, so do murder rates, right? But they aren't really connected. I'm not saying that if we buy ice cream, we're going to murder somebody. I'm not saying that Mother's Day is coming up, we stop doing crime. No, wait, that is what I'm saying. But that one might not work. It's a third factor, right? The heat is Mother's Day. Yeah, oh my God, the heat is Mother's Day? That's what I just said. The heat is what's causing murder to increase and ice cream sales to increase. Because as it gets hotter in temperature, it's showing that ice cream sales are going to increase and we get more aggravated. So do murder rates. The Mother's Day one doesn't work. I lied. So coefficient of determination. This allows for comparisons between and among different correlations. Coefficient determination or of determination is saying like, okay, we found this correlation and now let's go compare between different correlations or among the different correlations. Okay, but correlations, they're all about the relationship. So we have a correlation matrix, which is the table to show all the correlations. These are the tables that I'm sure you've seen that have, they're like a square and like half of it, the top half up here is just blank because everything you're going to show down on the bottom half is going to just be mirrored on the opposite side. So yeah, that's correlation matrix. Then we talk about regressions, and this is where we're predicting the relationships among continuous variables. So a linear regression is a form of regression in which the values of the dependent variable are going to be attributed to one independent variable, right? So the independent variable is the one that we manipulate, we change, and then that has effects on the dependent variable. So if I change something in my independent variable, I'm going to see the values of my dependent variable shift based on that one independent variable, okay? A regression line is a line that's drawn through all of our data points on a scattergram. So it's just like a bunch of data points like all over. And then you draw a line that's the best fit to try to summarize that relationship between independent variables and dependent variables. Okay. Beta coefficients or beta weights, these are the standardized scores, again, to show this is not due to chance. This is legitimately the effect we saw, and it's a legit effect, not due to chance or due to the fact that we had 10,000 people in a population. Okay. A multiple regression. We use this to test for significant relationships between the dependent variable and multiple independent variables. And we can do this separately and as a whole. So what I mean by that is any changes we do in the independent variables. So it might just be, I'm not manipulating the independent variables. It could be a natural manipulation of political affiliations, political involvement, stuff like that, right? I'm not manipulating it. I'm not saying, hey, go home and watch all this stuff. I'm saying this is going to manipulate just based on people's independent uses and levels of politics, right? So I'm going to say that anything we see happen to the DV is going to be attributed to both or all of the independent variables, okay? We have a multiple correlational coefficient, and this is an index of the magnitude of the relationship among variables. So it's taking all the correlation coefficients, and it is saying like, this is the magnitude of these results. This is the magnitude of these relationships. Again, I'm not super great with that one. I'm good with correlations, but the correlational coefficient is not something I've used much in my research, if ever. We talk about hierarchical regressions. So we use these to enter independent variables in the order or sequence in which the variables are going to influence the dependent variables. We group them in sets or blocks, and this is based on the research that we've done. So if I think that gender is going to have the most impact on willingness to share political information, right? I think gender is going to have the most impact. I'm going to put that one in first. And then I might put in age. And then I might put in Dunstan, nibs only. And then I might put in your frequency of affiliation or something like that, because that's the order that I think it's going to be influencing their willingness to share political information. Then we talk about a stepwise regression. So the independent variables are entered in sequence or order, but it is determined by the statistical program, not the researcher. So a stepwise is just saying, these all are going to influence it, I think. You tell me which one influences it most. So you put them in the same set or block, okay? Now we're getting into chapter 13, the results section. So the results are presented as information without interpretation. So you include the statistical test, what it was, all the variables, the results of the test, and then you write a written description connecting the result of the statistical test as support for or rejection of the hypotheses. And then you can also give the answer to that research question if that's what you did instead of a hypothesis, right? So the results section, there is no interpretation. You are strictly giving them facts. The discussion section, however, the researchers are going to provide their interpretation of the results based on their research questions or hypotheses in the literature review. So the discussion section, I recollected data on my dissertation. I said that people who are listed as opioid use disorder or people having opioid use disorder versus people who are addicted to opiates would be better, because I said that OUD, opioid use disorder, is better than being called an addict. My problem was I called them people. I brought the human quality back. Shame on me. I'm just kidding. I love that that was an issue for me that I immediately called them people with. I liked that. But I had to recollect data, and in that I had to say people who are addicted to opiates versus addicts, because I want to see the linguistic differences, right? So my results section, I didn't find what I was looking for because I called them people. So I can just give the results of the statistical tests. The discussion section is where I said, hey, it was a people first linguistic issue. So PFL is person first language, which brings back that human quality, right? So I can put that interpretation in there. I can say that, but I can't do that in the results section, okay? All right, so that is the end of our module 5. If you have any comments, questions, or concerns, please don't hesitate to reach out. And if you are using the quantitative analysis, you will do this week's quant analysis worksheet. If you are not, you will not. You will do next week's. But everybody has to take the quiz. Okay, so as always, reach out with any questions, comments, or concerns, and I will see you next time.